I hope that most of you brought your computers today. It'll be useful if you have them today. You can go ahead and get them out, get them booted up. Some computers take a while, I realize. It's going to be even more important to bring them on Monday. So if you don't have one today, that'd probably be all right. But please, if you're able, bring a computer to class on Monday. Also on Monday, homework 4 is due. I'll take the key home with me over the weekend, just in case if you have questions, then I'll be able to do my best to respond. I sometimes get questions like, what should I use for I on question 5? And I'm sitting at home laying on the couch with my phone and I'm trying to remember what's question 5. But I'll be prepared this weekend in case you need to ask me questions. I also have office hours today, so feel free to stop by. So any questions related to these announcements? All right, we're going to jump right into some in-class exercises I'm going to teach through doing today. We're going to start off by looking at a gradient. Remember, the arithmetic gradient is the one where the amount is increasing each year by a constant amount. This one has a twist, though. It's not just a gradient. It's also an annual series on top of the gradient. So this is going to be a two-part problem where you have to find the present value of a couple of different pieces. First of all, you have to find the present value of the annual series. What is the amount of the annual series? Can you see it? Is it jumping out at you that this has two components? What's the amount of A? Anyone know the G? You know the amount of G is obvious because it says right there, G equals $30. A is 400. Why do you say that? Good. That's right. So think of it this way. Here is the A that the G is built on top of. I'm drawing it on the screen here. All right. So there's a constant A. Every year there's 400, but then in year 2 is when we see this extra 30 kicking in each year. And so here on the in-class exercise handout I've given you, I ask you to use the equation formulas to find out what is the present value of these future deposits that you're going to have to make in years 1 through 5. Now, in case you don't have that formula sheet handy that I handed out last time in class, let me take the screen back to those formulas. All right, here they are. So we are going to find P given A and also find P given G, and then those two things together will be the combined present value. So find P given A. So P slash A is here. So we're going to use that formula. That's a tricky one. And then find P given G. Oh my, that's even worse. Look at this formula. It's like a nightmare. But you can do it. We'll use the computer most of the time. We'll use the table lookup factors most of the time. But I'd like you to get at least a handful of opportunities to try out some of these less simple equations. For those of you in the back, let me try and zoom in on that a little bit so that you can see it more easily. So find out the value of P. So I broke it up into two parts, and I said that part 1 is dealing with the annual series, so trying to find the present value of that 400 that comes in, well, it's going out every year, the 400 of every year. And so the formula for that is here, this factor formula. I'm going to find some amount, and that amount is the ratio of the present value to the annual value. So 3.60478, that is the present value relative to the annual amount, which is why when I multiply by the annual amount of 400, I get the present value of 1441.91. Part 2, remember we see the gradient start to kick in at the end of the second year. So it's 0g for year 1, then g, 2g in year 3, and so on. And so the equation is complicated enough that it's easy to make mistakes. That's why I kind of do it in stages. You know, I've got two different components here, one minus the other, and so I solve for them separately. The 30.04 is the result of this first expression. The 23.64 is the result of the second expression, and then I combine them here as the factor, 6.3970 multiplied by the 30, and then combine the two present values together is the 1633. So now you've used those ugly equations. Maybe in the future you'll just use Excel or use the factor lookups, but these are helpful especially when you've got an odd interest rate. You know, there isn't going to be a table in the back of your book for 7.2%. There'll be some of the even numbers, but some of the more odd interest rate amounts, you'll just need to solve for them yourselves. Any questions related to the first part of this in-class exercise? Let's look at the second question, and this is where we're going to start to use Excel. Okay. That's not the one, right? No. Ah, okay. Here it is. Question 2. A contractor purchases equipment for $60,000 and it's going to provide an income of $16,000 a year for 10 years. So the first thing I ask you to do is draw the cash flow diagram on the paper. And once you've got that, I'm going to show you how to set that cash flow diagram up as a table on Excel and how we can start crunching the numbers. So just draw the cash flow diagram described here. All right, so hopefully your cash flow diagram looks a little bit like this. The present value of $60,000, a purchase, that means that this contractor is investing some money. So it's an outflow because of the purchase, and it's going to allow for more income. So I have 1, 2, 3, 4, and I could have just continued with all 10 lines, but this little ellipsis here, the dot, 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 indicates that it continues with the same exact trend until the terminal year of 10. So it's relatively simple. So the question it's asking is, what's the rate of return? What's the I? And there are several ways that we can do that. The first of them is we could say for a certain p-value, all right, we have the p is 60,000. So here is p, 60,000, and then here's A. So we could say the ratio of P to A is 60,000 to 16,000 with n equals 10. So what you could do is you could go to the back of the book and you could go through all of the tables and find out for the column that says P to A, solve this, 60 divided by 16, get the ratio, and try and find where in the tables for the row of n equals 10 do you find that ratio equal to that. And that would work if it's an exact solution. If there happens to be, like if it's right on the money, 6%, 8%, or so on. But more easily, we can set it up as a spreadsheet in Excel. So if you have Excel, go ahead and start it up and follow along with me. What we're going to do is translate the cash flow diagram that you just created into a table. All right, and we're going to have the following column headings. We're going to have, first of all, I equals, and then we're going to leave that blank for now. Here, let me make it a bit bigger so that you can see. All right, we're going to have year, amount, and then PV of the amount. PV stands for the present value. And then we translate what's in the cash flow diagram into a table. So we had years 0 through 10. And so I can type in all those numbers, or I can highlight the first two and then drag downward, and it continues the trend until I hit 10. So you just have all those years there. And then we type in the amounts. The first one is negative 60,000. And then the rest of the time it's 16,000. Positive value, meaning that it's an inflow. And rather than typing that in over and over, what I'm going to do is just drag downwards, and it continues the trend. So see this little green box in the corner? I'm going to click and drag that green box. Since we're working on Excel now, I'm going to remind you that all these lectures are recorded. So if you fall behind or you didn't bring your computer and you want to try and go through this again later, you can easily bring the video up and play it as many times as you'd like to catch all the tricks that I'm going to be showing you. All right, so there's a function in Excel that finds the present value, and the function is called PV. So let's just say, let's have some guess value of our interest rate. Like we're trying to find in this problem, it's asking what is the interest rate that makes it so that 60,000 in the present is worth 10 payments of 16,000 in the future. It's asking what's the interest rate that brings those two things into balance. And so we don't know the interest rate. This is our unknown. And so the interest rate that we're going to start off with, just as a guess, maybe we can say maybe it's 0.05. That would be 5%. So I'm going to do this function, equals PV, and then it's going to ask me little questions. Equals is a way of telling Excel that you're starting a formula. PV is one of its pre-existing formulas, and as soon as you start typing in a pre-existing formula, then it's going to give you the option of following along with the formatting. It's going to give you little prompts. And so you can't see it maybe in the back, but it has these little prompts, and in bold it's showing you the one that it wants to see next. And so it's saying, what is the rate? So I'm just going to click in the cell location where the rate is. I could type it in. I could type in 0.05, but the problem with doing that is that it wouldn't automatically update in the same way as if I just click in a cell location, it will automatically update. So I click here, and now it knows that that's the interest rate. And then the next thing, when I put in the comma, it's going to say NPER, and that's its way of asking what year is it. And so it's year 0 when we're in this row. So I'll just click in that cell location. Now I click comma, and the next thing it's asking is what is either the payment or the future value. And this is saying payment. So if I click on this amount right now, it's going to think that that amount is every year it's that amount, over and over again. But this is just a one-time amount. Each row represents the amount just for that year. So I'm going to put in another comma to skip over that field, and you'll notice that now it's saying what is the future value. And this 60,000 is the future value. it's in year 0, so it's really a present value, but it's okay for us to click that. It's still going to discount it for 0 years because we've clicked on year 0. Now there's two more things that we're going to do to make it easier on ourselves. One is that we need to put a negative sign in front of that B5, which is the amount. And the reason why is these pre-existing Excel formulas sometimes automatically are set up to change the sign of things. They're saying, well, if you make a payment, then you should get a withdrawal in the future. So Excel's trying to outsmart us in a way, and so we have to cancel that out whenever we use this present value function by putting the negative sign in front of the amount that we select. And then the other thing has to do with, we don't want to type this formula in over and over and over for each cell. We want to just drag it down and have it automatically fill that formula in. And it can do that, but if we just drag it down, all of these letter and number locations are going to be relative references. And so it's going to work great for the amount and for the year. You know, when I drag that down for the next row, then it would start looking here at this amount and that year. And that's what we want. But one of those things, we want it to always be the same amount, and it's the interest rate. We always want it to look at the location for the interest rate. We don't want it to start looking lower than there as we drag the formula down. So there's a way of doing something called anchoring the cell. And so I'm going to go back to this location where the interest rate is specified. You can either type it in manually, $ tells it to anchor, or you can just press the F4 button. And as I press F4, it automatically puts those $ in there. And so $B, $2 just means I'm always going to keep looking at that same location. And I've just poured a lot of information all over you. Don't get nervous if you haven't followed all this straight away. We're going to come back to this over and over through the semester. So for some of you, this may be second nature already. Some of you, it may be a little bit awkward. Okay, red with the brackets is a weird way of it saying that that's a negative amount. I'd rather see it as a minus sign instead of red with brackets. And so I'm going to change that to this currency, and then I can live with that, the way that it's formatted. Now here's the exciting thing. Rather than having to type that equation in over and over and over, I'm going to just click on the corner and drag it down. And if I've formatted everything correctly, what it's doing is it's calculating the amount of each of these, the value of each of these different rows in present terms. And so the 16,000 that we get in year 10, in today's terms, that's only worth 98.22. But that same quantity of money, the same 16,000 in year 5, is worth more in today's terms. So does that make intuitive sense to you that, like we've said lots of times before, money in the future is less valuable than money now? Or money more in the future, like year 10, isn't as valuable as money not so far in the future. Look at year 1 and year 2. That 16,000 isn't discounted as heavily. So now I think by looking at this, you can get an idea of what this word discounting means. It means you're reducing the value of some future amount to the present. Okay, now what we need to do is find the total. So I'm going to call this the sum and use the formula equals sum and add up all of these amounts. So I'm just scrolling to include all of the amounts year 0 through year 10. Now what that tells me, the fact that it's not 0, it tells me that I don't have the right guess value for I. So my goal is that this amount should be 0 if future value and present value is in balance. So let's go back to the original problem statement. It was asking basically, what's the interest rate that makes this present value of 60,000 equal to all those 16,000s that we're going to get for 10 years? So it's not 5%. We can say, what about 6%? Well, it's getting closer. Remember, we're looking for this to be 0. What about 10%? Okay, we're getting closer still. 20%? Okay, getting closer to balance. So we can just play around with this, and we're getting awfully close now to 0. There's a way to kind of like automatically search, and it's here under, let's see, data, what if analysis, goal seek. And what I want it to do is I want it to let this one, I'm trying to make it that one be equal to 0, and I'm giving Excel permission to play around with the interest rate until it equals 0. So I say go for it, and then it finds the exact interest rate that to the dollar makes the inflow and the outflows equal. All right. That was a lot. But the good news is by the end of the semester, you're going to really find this quite easy. So that's one way of finding the rate. The question on the handout that I gave you is, what rate of return did the contractor realize on the investment? So the rate of return is 23.4%. You get 23.4% if you make a deposit of $60,000 and then you can make 10 withdrawals of $16,000. That's a wonderful rate of return. You could certainly not get that rate of return in a bank, 23%. But maybe there's a contractor out there who can buy equipment for $60,000 and then make all these withdrawals or additional income from having the equipment, and it yields 23.4%. There's always an easier way when it comes to Excel. And I want you to know what's going on in the background. So I'm going to force you to learn and understand and duplicate the method I've just showed you. But I want to make you aware of the fact that there's another function out there that's called rate. Let's just explore that function. Equals rate. Okay, now it's going to start asking some questions. First of all, NPER. That means how many years? There were 10 years, so I'm just going to type that in. All right, now it's asking what was the payment amount? So how many times did we see, 10 times we saw what payment? It was 16,000. Okay, comma. Now it's saying what was the present value? Our present value was negative 60,000. And now we can close parentheses, and it calculates for us, and it says that's a 23.4% return. So that rate function is pretty handy. You can't always use the rate function, and sometimes in the more complicated analyses we'll do in a few weeks, you have to have this step-by-step set up to be able to do further calculations, but that rate is awfully useful. Any questions so far? All right, turn the page over, and we have the last question on the in-class exercise. It says, a contractor buys equipment for $60,000 and it provides income of $8,000 per year. At an interest rate of 10% per year, how long does it take to recover the investment? So we're asking how many years rather than what's the unknown interest rate. Let's set that one up here as a table. What that looks like as a table is we know the interest rate. Okay, so we have I equals 0.1 for 10%. Now we're going to have year. Let me make that a bit bigger so that you can see it. All right, year, amount, PV of amount, and then something we're going to call the cumulative PV of amount. All right, so the year start at 0 and go through, we don't know exactly how long it's going to take. Let's drag that down through 17 years, just to be sure. All right, so now for our amount, we're going to translate the problem statement. The investment was $60,000 to begin with, and then the income is $8,000 per year. And that just is continuous. They never tell us when the equipment wears out or when the payments stop. All right, PV of amount. You saw this on the last problem, so we're going to use equals PV, refer to the rate by clicking on that location and pressing F4 to anchor it, comma. Now NPER, it's asking how many years or what year is it, so it's year 0 here, comma. Now it's saying what is the payment. We have to skip over that because each one of these represent not an ongoing payment, but each individual row is just a single year. So I'm going to skip over that to the future value column and put negative of the amount. Close parentheses and enter. I'm going to change the formatting that I like to currency. All right, so the present value of 60,000 is 60,000. So far, so good. Let's drag that down one more. So the present value of 8,000 is, in year 1, is 7272, so that's good. I can just double click on the green box and it will fill that in all the rest of the way down through the table. So I don't even have to click and drag. I can just double click in the green box and then it spreads that down. And then finally, cumulative present worth. So at year 0, all we've got so far is we're $60,000 in the hole. But now at the end of year 1, we've recovered some of the $60,000 that we invested. So the cumulative present value is the $60,000 from the previous year plus the amount that came in this year. So the cumulative present value, now we've recovered a little bit of the money, but we still haven't got back all of our investment. So I can click and drag this down and it's going to apply the same formula. And what you'll notice is that gradually our debt is getting lower and lower until after 15 years of operation we finally have a positive amount. That means that whoever did this deal, whoever bought the equipment for $60,000, has to keep that equipment in operation for 15 years in order to break even at an interest rate of 10%. All right, so some of you don't have computers. Some of you who do have computers maybe didn't follow along with what I just did. It's really important that you understand how to do it. So if you didn't do this or you fell behind, please watch the video over the weekend and duplicate the same moves that I just demonstrated for you. You can hang on to the in-class exercise, of course, but it'll really help you out. Feel free to check your homework using that method, but the assignment that's due on Monday, I think all of those problems are specified as hand calculations. And so do it by hand, but then feel free to use Excel if you find that's helpful. So that's it. I'll see you on Monday. Have a good weekend.